Entrant, Terraforce. Project name, Bangalore International Airport. Owner-occupier, Bangalore International Airport. Architect, Grant Associates and Design Accord. Engineers, Fred Laker, ICOS Engineering, Struct Geotech, Macquarie, Smart Mines, Stup India Private Limited. Main contractor, Balaji Infratech and Constructions Private Limited. Subcontractor, Hariali Landscapes. Precast manufacturer, Terraforce. Terraforce, a long-standing Concrete Manufacturers Association member, supplied over 110,000 L12 blocks for the construction of retaining walls on both sides of Terminal Boulevard, a newly constructed 10-lane thoroughfare, which feeds directly into India's Kempegowda International Airport at Bengaluru. After considering various retaining wall options, the Bangalore International Airport Limited project team chose the Terraforce retaining wall system for several reasons, aesthetics having been a major consideration. The blocks also allowed the planting of flowers and other vegetation, and the inclusion of hewn pipes facilitated the planting of trees. In addition, the Terraforce option required less soil excavation and was more cost-effective than either reinforced concrete or reinforced earthen walls would have been. Completed in November 2022, Terminal Boulevard has been widened from 2 by 2 lanes to 5 by 5 lanes, to cater for the addition of a second airport terminal and an anticipated increase in traffic. Approximately 1.2 kilometers of the road has been lined with retaining walls on both sides, which cover a total surface area of 9,000 square meters. Running on an east-west axis, the new road was constructed by cutting a corridor, which at its deepest is 9 meters below existing ground level. This has enabled the new road to pass under the airport forecourt roads to facilitate junction-free traffic flows. The excavated corridor resulted in embankments which varied in heights of between 0.5 meters to 9 meters and in slope angles of 52 degrees to 77 degrees off the horizontal. The slopes were cut to allow for the insertion of 5-meter hewn pipes to facilitate planting of trees on the vertical slope at every 4 meters. Placed on concrete foundations, the pipes were filled with soil, and the bottom ends of the pipes were kept open to allow for root penetration into the soil below. Where additional cutting was required, for instance, near bridge abutments or the retaining wall ends, these sections were backfilled with gabion blocks and cladded with Terraforce blocks to maintain the required slope angles. A main challenge was that additional cutting into the embankments for the installation of geogrid reinforcement was not possible. This was because the top sections of the excavated embankments were only 2 meters from the upper level roads, and there was no space left. In addition, the required loading on these roads was up to 45 tons, 4 fire brigade trucks, and other heavy vehicles. Therefore, soil nailing was specified as an alternative to geogrid to keep the slope stable. This involved drilling 115 mm diameter holes of up to 9 meters in length, perpendicular to the slope of the embankment. Nails, 28 mm in diameter, were inserted into the holes and grouted with a non-shrinkable cement slurry. Once the nails had been inserted, PVC drainage pipes, up to 2.5 meter long and wrapped in a geotextile membrane, were installed in pre-drilled holes in the embankment at a slight upward incline to the horizontal plane. The drainage pipes were installed in a grid of 3 meter by 2 meter to release entrapped water and to reduce the hydrostatic pressure in the embankment. The slopes were then covered with layers comprising a geodrain membrane, 2 layers of 8 mm steel mesh, and 100 mm of shotcrete. The geodrain membrane was installed to prevent the leaching of soil and fine material. Steel plates with metal hooks were bolted to the nails and tied to the 8 mm steel mesh layer with 100 mm shotcrete. The hooks were used for tying to a second layer of steel mesh, after which a second 100 mm layer of shotcrete was applied. The steel plates ensure the nails are affixed firmly to the steel mesh and the shotcrete layers to form a monolithic structure and to prevent the nails from penetrating through the wire mesh and the shotcrete layers. Reinforced concrete shear key blocks, which arrest both the vertical and lateral forces acting on the Terraforce blocks, were cast to form the foundations of the Terraforce walls. Steel rods were inserted into the hollow portion of the blocks for interlocking between each vertical layer of blocks, and the spaces between the block facades and the shotcrete layers were filled with lean concrete. The bottom block rows followed the slope of the road, and similarly, the top rows were adjusted to match the profile of road or the ground at the upper level. This was done either by stepping the top row or by adding a concrete layer to match the required road or ground profile. The sections between the top of the Terraforce walls and the upper-level road curbing was paved with precast concrete paver blocks to prevent water ingress into the retaining wall structure and the soil behind it. However, any water trapped within the embankment structure will drain through the PVC drainage pipes. Some of the other challenges were the varying friction coefficients of the embankment soil, which was the deciding factor in determining the length of nails, and managing the levels of the walls when both the top and bottom roads sloped at different angles was another.